All right, so today we are talking about normal distribution. This relates back to what we were talking about before with skew, where if data was heavily weighted towards one side or the other, it was considered skew. If everything is distributed evenly, then it is considered a normal distribution. Now, before we start getting into the specifics of that, I want to make sure that we understand a phrase that we're going to see a lot of, which is finding the number of standard deviations that data is from the mean. So we know what standard deviation is. We know what mean is. It's a pretty simple calculation. Basically, if they ask you to find a number that is a certain number of standard deviations from the mean, then we just add or subtract the standard deviation that many times. So in this first one, it says the heights of students have a mean of 66.5. You will often see this written with a little mu symbol. The standard deviation is 4.5. Again, we said for standard deviation, we're going to use the lowercase sigma. If we want to figure out the height of a student that is one standard deviation above the mean, we're going to take whatever our mean is, and we're going to add the standard deviation to it once, and that would tell us how tall this person is. If we want two standard deviations below the mean, we're going to take our mean, we need our number to lower, and we need to subtract the standard deviation twice. And there we go. Alright, so this is going to be important for when we are analyzing our normal curve in a moment. Alright, so we said before that if your mean, your median, and your mode are all the same, it is normal distribution. When you plot your frequency curve, you're going to get something that looks exactly like this. This is typically referred to as the bell curve because it looks like a bell. What do we know? Again, if everything is situated towards the middle, then there should be an equal amount of data on either side. So the midpoint of the whole thing is the mean, the median, and the mode. Which again means exactly 50% of the data falls on either side. We also know that the standard deviation is going to tell us where 68% of the data falls. Right? So 68% of the values will always fall within one standard deviation of the mean. We also notice that if we collect all the data within two standard deviations, that represents 95% of all of our data. And then 99.7% is represented by 3 standard deviations. So you can kind of see how we're using our standard deviation to break up the curve, to break up our data, and we can use those percentages then to calculate the probability of finding certain values in certain ranges given our data. Alright, so how are we going to do that? Well, first of all, they're always going to give us some information about our data. So we know our mean is 75. We know our standard deviation is 5. We want to know what percent of students scored between 70 and 80. So oftentimes you will see this calculation written out like so. We said to figure out the number of standard deviations, we would just add or subtract that to the mean. So if I'm working it backwards, I subtract the mean and the standard deviation to figure out how far apart they are. And then I divide, fix that real quick, by what the actual standard deviation was to figure out how many standard deviations it is. In other words, my mean is 75, and I want to know how many people are at between 70 and 80. Well, 70 is what we're looking at. 75 is the middle, and my standard deviation is 5, so that's -1. Looking at our bell curve before, right, the -1 is here. If I go from 80 I get +1, which is here. And so from before, we said that there is a total of 68% between the -1 and +1 standard deviations. So in other words, there should be 68% of all test scores should be within 5 points of the average. If I only look at it from the perspective of 70 to 75, I'm basically looking at -1 up to the middle, right? So when I look at my curve, instead of going all the way to 1, I stopped here. And I know if my data is symmetrical, that 68 just divides in half, so there's 34% here and 34% here. So that means 34% of all people who took this test scored between a 70 and 75. All right, so again, 0 and 75. Well, we said 75 was the mean, so 75 is exactly in the middle. We also know that 0 is the lowest possible score we can get. So we're basically going all the way from here to here. And since our data is normally distributed, we know that exactly half of the numbers are on the left of the median, so 50% of our test takers scored less than 75. And finally, to go from 0 to 80, we said 75 was in the middle. Our standard deviation was 5, so 80 is exactly 1 standard deviation away. There's 50% over here. There's 34% over here, again, because we split the 68 in half. So that means there is a total of 84% of all test takers who scored between 0 and 80. All right, and our last example, we're going to look at how to convert these percentages into probabilities. And we know that probabilities themselves are percentages. When things are not exactly 1 or 2 or 3 standard deviations away, we're going to have to use a conversion table to figure out what percentage matches up with a certain number of standard deviations. The good thing is our calculator can do this for us. So if you notice, there is a button that says distributions. When we hit that, we're going to notice the second option says this. It means we want a normal distribution. The C stands for cumulative. So in other words, since we're looking at ranges, we want a cumulative distribution as opposed to a specific single point, which is what the P would give us. So we are most likely never going to use the first option. We're only going to use the second. So when you do that, when you hit that button, what it's going to do is bring up a screen. It's going to ask you for 4 things. You need to know the lower bound, the upper bound. You need to know the average and the standard deviation. So if we give it all 4 of these, what it will do is calculate the number of standard deviations the 2 values are from the mean, and then it will convert those into percentages for us. So if I want to find the probability that an egg is a medium egg? I'm going to look at my little table of data. I know that a medium egg is between 53 and 63 grams. And according to my setup, I have a mean of 55 grams and a standard deviation of 7. If you're using a different calculator that does not bring up this little menu where you see all 4 of these guys listed out, you simply place them in order separated by commas. So we would type normal CDF 53, 63, 55, 7, and it will spit it out. So when we hit enter, and then possibly enter again, depending on whether it calculated it for you, you should get something that looks like this. So 0.4859, which means we have about a 49% probability that the egg is medium. All right, so for extra large, notice we have a minimum value, but not a maximum value. So since you cannot type infinity and we don't have a maximum, you're just going to want to type some very large number. So we usually do 1 times 10 to the 99th power, which will be gigantic enough to get the information we need. But we're still using the same set, so the 55 and the 7 will be the same. And if we do that, we should get 0.0051, which is about 0.5%. And then finally, they give us a number of eggs, and they want us to estimate the number of large eggs. So this goes back to our expected value we were talking about. We need to figure out the percentage of eggs that will be considered large, and then you combine that with 2,000 to get the total. So if you go back to the calculation we were just looking at, using 63 and 73 as your lower and upper bound, you should get something that is about 0.1214, which means about 12% of our eggs are large. So we're just going to take that, multiply it by the total, which means about 242.96 eggs will be large, so we can go ahead and round that off and say that's 243 eggs. All right, that is all for today. I will see you next time.